So in this practice, I'd like to introduce the Roche limit of an object. But first, we'd like to review the tidal force. So tidal force appears when we consider the finite size of the object is rotating around the same central object. Tidal force is directed out of the object with this F tidal. For the unit mass, tidal force is given by 3 omega squares delta r. Delta r is the size of the object. If you consider the distance from the central object to the rotating object, the capital R, omega is given, omega square is given by gm over r cube. So you can substitute these equations here. So this becomes 3 gm over r cube delta r. So if the distance from the central object is decreasing, then F tidal force is increasing. This is a characteristic of the tidal force. If the tidal force is r distance from the object, central object is type of the functions we'd like to consider tidal force. Then we'd like to consider the unit mass of the object is attached to the rotating object, central object, and the rotating object. And the sum of the unit mass of the object is attached to the outer edge of this object. Actually, two forces acting. One of the forces is the tidal force. If you consider the mass of this small object m sub 0, F tidal, it becomes 3 times g m over r cube delta r times m sub 0. Right? This is tidal force is acting outward from the center of this object. And another force is acting, the gravity. Gravitational force to the center of this object. So F grav is g, mass of this object, mass of this object is m times m sub 0 over delta r squares. This is the gravitational force acting between the small mass of the object m sub 0 and the mass of the object, rotating object m. Then we could compare the two forces, tidal force and the gravitational force. As I explained, if you draw the horizontal line distance from the central object, then tidal force is decreasing function with r 0. This is F tidal. And in the gravitational force, this gravitational force is independent of r. So gravitational force is a constant because it's not related to the central object. Then you might find out This is some kind of the threshold. In these regions, in the outer regions, F gravitational force is larger than the F tidal force. In the inner regions, F tidal force is larger than the gravitational force. Then what this means? Gravitational force is larger than tidal force. This m sub 0 is attached to the rotating object. So the object is safe to keep its shape. But inner regions, in this case the tidal force, is larger than gravitational force. This means tidal force overcomes the gravities in the close orbit. It's difficult for the object to keep the shape. Impossible to keep its shape. Because the tidal force is stronger in this region. So in this region, tidal force is stronger than the gravitational force. As a result, this object has to move away from the object. But outer regions, gravitational force is much stronger than the tidal force. Then this object can stay on this rotating object. So it keeps its shape. Then actually at this point, F gravitational force is equal to F tidal force. So we call that this position we call the Roche limit. Outside of the Roche limit, gravitational force is stronger than the tidal force. The particle can keep its shape. But inside of the Roche limit, particle cannot keep its shape. It's broken into the small pieces. This is a Roche limit. And by equating these two equations, F gravity is a gm over delta r squared equals 3 gm over r cube delta r. So from this equation you can find the Roche limit. Is equal to 9m over 4 pi rho m over 1 over q. So this m is the mass of this object, can be expressed density times 4 pi over 3 delta r cube. Then delta r is cancelled in the both sides of the equations. Then if you want to find the Roche limit of the Earth, R Roche, can be substitute mass of the Earth and the density is 1 gram per cubic centimeters. Then it becomes 1.6 times 10 to the 4th kilometers. And the density of the mass over 1 gram per cubic centimeter over minus 1 over 3. This is the typical density of the ice. So it's about 3 times the radius of the Earth. Whether this is a sign of the Earth. If you compare the Roche limit of the Earth, the orbit of the moons, distance to the moons, is 3.8 times 10 to 5 kilometers. This is much longer than the Roche limit of the Earth. So this indicates the moon is safe. The moon is safe from the disruptions. Okay, so this is the end of this practice.